In October of 2024, Tesla unveiled its long-anticipated autonomous taxi, the Cybercab, at its We Robot event. But the question remains, are these vehicles ready for real-world deployment? Or is this just another round of marketing hype designed to attract investors? In this episode, we dive deep into Tesla's journey, compare its technology to competitors, examine the legal landscape, and analyze the impacts of autonomy on society. Buckle up, you're in for a ride. Tesla has come a long way since its first battery-powered vehicle, but to truly understand its journey, we need to take a step back. Tesla was founded in 2003 by Martin Eberhard and Mark Tarpenning, with a vision of creating high-performance, net-zero emission vehicles. The timing couldn't have been better. Between 1996 and 1999, General Motors became the first major manufacturer to produce a purpose-built electric vehicle for consumers, primarily through leasing programs. The EV1, however, had significant limitations. It could only achieve around 60 miles between charges and would take 8 seconds in 0 to 60 miles per hour tests. Due to these constraints and high leasing costs, GM ended production in 1999. Despite promising not to recall the vehicles, they did just that in 2002, frustrating many loyal electric vehicle enthusiasts. Tesla entered the market with the promise of an all-electric vehicle, immediately grabbing the attention of electric vehicle enthusiasts. One of them was Ian Wright, who happened to be Martin Eberhard's neighbour. Wright, an avid racing fan, joined Tesla in 2003. In an interview, he recalled how it all started. The original conversation I had with Martin was over a beer at a party. He said, "I know you used to build and race cars, and my buddy and I have started a company. We're thinking of building very high-performance electric sports cars. What do you think?" I said, "I think you're crazy. They're only golf carts, aren't they?" Clearly, I was wrong. Elon Musk joined Tesla shortly after its founding, becoming a key figure in the company by injecting much-needed capital, even before Tesla had a product to show. His ability to secure venture capital funding in the early days was a game-changer for Tesla's survival. In 2008, just as the company had its first vehicle, the Roadster ready for delivery, Tesla was on the brink of bankruptcy. Musk personally led a crucial emergency funding round that saved the company from collapse. Shortly after, he took over as CEO, guiding Tesla through its financial crisis. His leadership not only kept the company afloat, but also laid the foundation for its future success, including its stock market debut in 2010. Finally, J.B. Straubel co-founded Volocom, a company focused on electric aircraft. He initially pitched Elon Musk on the idea of electric planes, but Musk wasn't convinced. What did catch Musk's attention, though, was Straubel's passion for long-range electric vehicles. That shared vision led to Straubel becoming the 5th key member of Tesla's founding team. Straubel played a crucial role in Tesla's battery development, overseeing the design that prevented thermal runaway. In simple terms, that is to prevent the batteries from overheating and catching fire, a major safety challenge in early electric vehicles.
Some of the challenges of working with lithium-ion batteries have been making sure that the batteries are safe in the automotive environment. That's really one of our biggest hurdles. We have to think of all different types of crash scenarios, different ways that the electronics might fail, and different ways that the packaging might be compromised. So there's really a lot of what-if type of engineering, and then designing around that to make sure that we've covered all the different scenarios and made a battery pack that is very safe under all the operating conditions that are possible.
He was also a driving force behind Tesla's charging network. While Musk initially pushed for battery swapping stations, Straubel saw a better solution: a dedicated network of fast charging stations. That decision proved to be a game changer, as today Tesla's charging network is one of its biggest advantages, so much so that it's now open to other electric vehicle manufacturers. Straubel also spearheaded the creation of the Nevada Gigafactory, which became a key piece of Tesla's expansion. It wasn't just about making more batteries, it was about making them sustainable, with a focus on recycling lithium batteries to reduce environmental impact. His work didn't just shape Tesla's success, it helped lay the groundwork for the future of EVs and autonomous driving, ensuring that Tesla's self-driving ambitions weren't limited by battery constraints. Martin Eberhard and Mark Tarpenning had discovered that outsourcing car chassis production was a fairly common practice in the automotive industry. This realization would become a pivotal moment in Tesla's early strategy. While attending an LA car convention in 2002, the two co-founders saw an opportunity. In an interview with CNBC, both Eberhard and Tarpenning recalled the moment they approached Lotus to discuss a potential partnership.
And hunted around and found the Lotus booth and basically forced ourselves upon the Lotus people. We forced him to sit and listen to our presentation, which he did, and was intrigued.
Yeah, was intrigued enough that he said, well, come to Hethel, which is in England, and we can talk more about this, basically. And I think that was a great gatekeeper, because anyone who wasn't serious wasn't going to fly to England, and go do that. But of course we did. Lotus was able to write a letter for us that said, if this company can do what it says and gets funded and everything else,
we'll be their partner.
We might be their partner.
Yeah.
Might. I mean,
it wasn't legally binding, but yes.
But it was what we needed, though, to show investors that we had a plan. We had a
Lotus, known for its lightweight and agile sports cars, had a chassis that seemed perfect for Tesla's vision. Rather than building an entire vehicle from the ground up, Tesla could adapt an existing chassis modelled on the Lotus Elise with a carbon fibre body as opposed to aluminum, and focus on what truly set their cars apart, the electric drivetrain. This partnership laid the foundation for what would become the Tesla Roadster. By 2008, Tesla released its first all-electric vehicle, the Roadster, a car capable of 0 to 60 miles per hour in under 4 seconds. Compared to the EV1's 8.4 seconds and limited range, Tesla had revolutionized what an electric car could be. Central to the core beliefs of Tesla's founders is what has been dubbed the Master Plan, announced to the public on August 2, 2006, prior to the release of the Roadster. In this document, Elon Musk alludes to the Roadster being developed to prove that electric vehicles can perform just as well as high-performance gasoline sports cars, before shifting focus to more affordable family vehicles. In essence, Musk's idea was simple: silence the biggest critics first. By proving that an electric car could handle high-performance racing, which demands significant power, then casual everyday driving should be a non-issue. The company's mission was to sell the Roadster at a premium price, using the funds to research and develop a more affordable yet luxurious car, and then reinvest profits from those sales to produce a truly affordable mass-market EV. All of this while maintaining a commitment to net neutrality, recycling, and renewable energy sources. And we now know this plan worked. The first step of this vision materialized in 2012 with the release of the Tesla Model S, a luxury sedan designed for corporate users, business professionals, and families. 4 years after the Roadster, Tesla was making its mark in the mainstream market. Around this time, Tesla also began deploying its first set of superchargers across 5 states in California. Fast forward to January 2025, and there are approximately 65,800 superchargers, with 7,000 stations worldwide. This is where things start to get interesting. In late 2014, newer Model S vehicles were built with the first generation Autopilot hardware, which included radar, ultrasonic sensors, and a single front-facing camera. However, the software that enabled these self-driving features wasn't released until 2015, about a month after Tesla launched the Model X. It was around this time that Tesla partnered with Mobileye, a company specializing in autonomous driving technology. Mobileye specializes in mapping and localization technologies for advanced driver assistance systems. The partnership was crucial for Tesla, as much of Autopilot's functionality was powered by Mobileye's IQ3 chipset. This chipset made it possible to implement key features like automated parallel parking, lane keeping assist, auto steer, lane departure warning, and obstacle detection. It allowed Tesla vehicles to monitor their surroundings, detect other vehicles on the road, and even provide warnings to ensure safer driving. In September 2015, the Model X went on sale, bringing with it Tesla's signature Falcon Wing doors, capable of opening in tight parking spaces, and a design focused on versatility. Unlike the Model S, which was a sedan, the Model X was an SUV or people carrier, offering configurations for up to 7 passengers, with lower-end options seating 5, including the driver. The Model X also introduced a more advanced sensor suite. It featured 2 cameras mounted on the windshield above the rearview mirror, one above the rear license plate, one within each door pillar, and one on each front fender. Additionally, an interior-facing camera was placed near the rearview mirror. Ultrasonic sensors lined the rear bumper for parking assistance, while a radar unit was integrated into the front bumper. Tesla's Autopilot system took driver assistance to the next level, expanding on existing cruise control technology. It introduced traffic-aware cruise control, which could maintain speed and distance from other vehicles, as well as lane-keeping capabilities that allowed the car to steer itself on highways, keeping canted within the lane, even around curves. However, Tesla's commitment to in-house technology eventually led to the end of its partnership with Mobileye, as the company shifted focus to its proprietary full self-driving FSD system. That said, Tesla has always been clear about Autopilot's limitations. The system can struggle with steep gradients, sharp turns, poor visibility due to rain, snow, or bright lights that dazzle the cameras, similar to the challenges human drivers face. Importantly, Autopilot was never meant to replace the driver. It was designed as an advanced form of cruise control, requiring drivers to remain alert and keep their hands on the wheel at all times. If the system detected that a driver was not holding the wheel, it would issue warnings. Failure to comply would result in the vehicle slowing to a controlled stop and disabling Autopilot for the remainder of the trip. In 2017, Tesla took its next big step toward mass market adoption, and in doing so, laid the digital groundwork for a future without drivers. The company unveiled the Model 3, a sleek mid-range 4-door sedan designed to make electric cars more accessible to the mass market. Under the hood, it featured what Tesla called Hardware 2.5, a modest but important update to its self-driving computer. While it didn't unlock full autonomy, Hardware 2.5 gave the car better processing power, improved reliability, and for the first time, the ability to support features like dashcam and Sentry mode. These features use the car's built-in cameras, originally designed for Autopilot, to record footage while driving or even while parked. One standout was Sentry mode, which turned the car into a kind of digital watchdog. If someone got too close, the car would record the incident, display a warning on the screen, and even send footage to the owner's phone, all using the same camera system that helped it drive. In 2019, Tesla made a major leap forward with Hardware 3. This upgrade replaced the NVIDIA-based system with Tesla's own custom-built chip, designed specifically for self-driving. It could process many times more visual data than previous versions, a leap designed to handle the demands of real-time autonomous driving. But this wasn't just about speed, it marked Tesla's deeper push into artificial intelligence. They had now built a proprietary computer designed not just to assist the driver, but eventually replace them. This was the beginning of what Tesla calls full self-driving, or FSD, and its camera-based approach known as Tesla Vision. The evolution continued in 2020 with the launch of the Model Y, a compact SUV that came equipped with Hardware 3 from day one. While older Teslas could be upgraded to the new system, the retrofit was only free for customers who had paid for the full self-driving package. For everyone else, it came at a cost. But not all of Tesla's decisions during this time were celebrated. In 2021, the company made a bold and controversial move. It began removing sensors. First came the radar, then the ultrasonic sensors, which handle close-range detection, were eliminated too. This raised eyebrows across the industry. Why remove tools that add extra layers of safety? Traditionally, self-driving systems rely on sensor redundancy, overlapping technologies that work together to interpret the world. Radar is great in fog or rain. Cameras give visual detail. Ultrasonic sensors help with things like parking. Take any of them away, and you remove a safety net.
Oh, whoa. Are you seeing what I'm saying?
Yeah.
I mean, that's pretty close right there. So as you guys can see, I use these ultrasonic sensors every single day with our Model 3. And as a lot of you guys know, Tesla removed all the ultrasonics from their vehicles, replacing it with a vision-based software using the cameras that are already on board. Today, I'm going to be breaking down why this is such a big deal, the cost savings for Tesla by doing this, and I'm going to be getting a brand new Model Y that does not have the ultrasonic sensors and compare it to our Model 3.
Gone forwards up towards this Mini, and the car says I've got 27, 28, 33, 34 inches, but it feels pretty close to me. Let's have a look. Right, so you can see here, like 20, it's settling around 22 inches. Let's have a look. That's not 22 inches, is it? No, it's about 2 inches. I'll go back and forward to see if it gives me a chance. All right. So let's just try this again. So there's that car in front. I'm manoeuvring around a car park. Let's have a look. So this says going forward is fine. I feel pretty close. You'll say, is that stop? Oh, this isn't, just flashed up 33 inches. I've got loads of room. I've got loads of room in front of me. There's 33 inches. Just about put my hand in there. So if the Tesla Vision doesn't pick up this car, then hopefully the sensors do. Oh, and that says 14 inches. Stop. Yep, so that's working. Yep, cool. Let's just test it wasn't a fluke, do it against another one. Again, bing, 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 and it says stop.
Since Tesla removed the ultrasonic sensors, it's become clear that the car struggles a bit more with accurately judging the distance to nearby obstacles. These sensors were particularly helpful when parking or manoeuvring at low speeds, close range detection where cameras can sometimes miss details. Interestingly, while the front cameras still face challenges, the rear camera system tends to perform better in judging distances. This is likely because the rear cameras are mounted near the number plate on the boot, offering a closer, more direct view of the car's rear boundary. In contrast, the forward-facing cameras sit higher up by the rear-view mirror, inside the windshield, which places them further back and higher than the front bumper, making precise distance judgment more difficult. But overall, relying solely on cameras means Tesla Vision can still have blind spots. This concern has sparked protests from some Tesla owners and industry experts, who argue that Tesla Vision isn't quite ready for prime time. Tesla's sensor strategy has led to reports of vehicles randomly swerving or making unexpected maneuvers. Issues with Autopilot and Tesla Vision have already surfaced from vehicles accelerating uncontrollably. In Columbus, Ohio, a Tesla Model 3 crashed into a building at 70 miles per hour. A similar scenario played out in China where a Model Y also sped out of control, killing 2 other people, whilst Tesla denied any fault with the vehicle, claiming the driver did not apply the brakes. In the WSJ documentary, data was extracted from the onboard computers, which provided a glimpse into what the vehicle saw and responded to before crashes occurred.
We can also see the inner workings of the most important Autopilot sensor, the car's cameras. The hacked data shows Autopilot recognizing and labeling objects on the road, judging their distance and position. Altogether, the data can show us what the car's software was seeing and the decisions it made in the lead up to a crash. On the morning of May 5th, 2021, Steven Hendrickson was driving his Tesla Model 3 to work. His car was in autopilot as he drove through Fontana, California. At about 2:30 a.m., an overturned semi-truck appeared in front of him. Moments later, he was killed.
The clips from the documentary by the Wall Street Journal highlight how cameras struggle in low visibility environments where often it's too late to act. Phantom braking occurs when the autopilot believes there is something in the way of the car's path and slows the car down. However, this has been known to cause rear-end collisions on motorways. To understand what makes a self-driving car truly autonomous, we need to take a step back for a moment. At its core, an autonomous vehicle is a robot. But what exactly is a robot? Simply put, it's a programmable machine designed to carry out tasks on its own. But there's more to it than that. A robot senses the world around it, figures out where it is, and makes decisions to move through that world, all without human input. It does this using a combination of sensors, which gather information about its surroundings, and actuators, which control its movements like steering, braking, and accelerating. In that sense, a self-driving car is just a robot with wheels, but with a far more complex job. Before we dive deeper into how autonomous vehicles see the world, it's worth taking a step back and looking at the bigger picture. How do we even define a self-driving car? To answer that, we need to understand the SAE's 6 levels of autonomy. At level 0, there's no automation at all, the driver does everything. Levels 1 and 2 introduce basic driver assistance, like cruise control or lane keeping. The car can help, but you're still fully responsible. At level 3, the car can handle certain situations on its own, but it expects you to take over if it gets confused. Level 4 takes that a step further. In specific areas, like a mapped city or a shuttle route, the car can drive entirely by itself. And finally, level 5. This is the dream. A car that can take you anywhere, anytime, with no steering wheel, no pedals, and no human intervention. But reaching level 5 autonomy isn't just a software problem. It requires the car to truly understand the world around it. And that's where sensors come in. To behave like a robot, the vehicle needs to answer 2 fundamental questions. Where am I? And what's around me? To do this, autonomous vehicles rely on a system called SLAM, short for simultaneous localization and mapping. It's the same principle that powers robotic vacuum cleaners and warehouse robots. As the vehicle moves, it builds a map of the world while also figuring out its own position within that map. At the heart of this system is something called an IMU, or Inertial Measurement Unit. Think of it like your inner ear. It senses rotation, tilt, and acceleration. In cars, it helps estimate how the vehicle's turning or tilting, even when GPS signals might be weak. It plays a key role in keeping the car steady and aligned in its lane. Then there are ultrasonic sensors, the short-range sentries of the vehicle. These are used for close-quarters detection, like during parking. They're great for spotting curbs, pedestrians, or other cars nearby. For detecting things further away, radar comes into play. It works like echolocation, bouncing radio waves off objects, and timing how long they take to return. It doesn't give you a visual, but it tells you something's there and how fast it's moving. It's like driving blindfolded, but using your ears to hear where things are coming from. Now, for a more complete picture of the world, we turn to Lidar, a laser-based technology that creates a detailed 3D map using millions of points, known as a point cloud. By firing laser beams and measuring how long they take to bounce back, Lidar can estimate distances with incredible precision. Lidar works by firing laser beams from a spinning sensor. Each laser beam travels in a straight line until it hits an object. When it does, the beam reflects back toward the Lidar sensor. The sensor detects the return signal and measures the time it took for the light to make the round trip. Since light travels at a known speed, approximately 1 foot per nanosecond, the system can calculate the total distance the beam travelled. By dividing this distance by 2, Lidar determines how far away the object is from the sensor. But there's a trade-off. While Lidar shows the shape and distance of objects, it doesn't reveal colour, text, or meaning. It's like seeing a world made entirely of wireframes. That's where cameras come in. They provide visual context, reading traffic lights, identifying road signs, recognising lane markings, and even distinguishing between a cyclist and a truck. In many ways, they're the car's eyes. All of these inputs, from the IMU to Lidar, radar, cameras, and ultrasonics, feed into the car's central computer, where an onboard AI interprets the data. Using deep neural networks, the system makes decisions in real time: when to brake, when to change lanes, or when to stop at a red light. But here's the catch. If even one of these systems is missing, the picture becomes less clear. And when lives are on the line, having an incomplete view of the world can be the difference between a safe journey and a fatal error. It's surprising that Elon Musk is so opposed to using Lidar in Tesla vehicles, choosing instead to rely on stereoscopic vision, pointing out that humans have 2 eyes, so vision alone should be enough to drive.
And in cars, it's freaking stupid. It's expensive and unnecessary, and as Andre was saying, once you solve vision, it's worthless. So you have expensive hardware that's worthless on the car.
People drive with vision only, no lasers are involved. This seems to work quite well. The point that I'd like to make is that visual recognition, very powerful visual recognition, is absolutely necessary for autonomy. It's not a nice to have. Like, we must have neural networks that actually really understand the environment around you. And Lidar points are a much less information-rich environment. So vision really understands the full details. Just a few points around are much, there's much less information in.
But is that really the whole story? Humans don't drive with just their eyes. We use our hearing to sense what's happening around us, rely on our sense of touch to feel the road conditions, and we adapt when it's cold or icy outside. All senses working together to keep us safe. Stereoscopic vision does help create a 3D understanding of the world, but even we struggle to judge distances perfectly with just sight. That's why we use tools like tape measures to get precise measurements. Similarly, Lidar and radar provide precise distance information that can be critical when lives are at stake. So, wouldn't it make sense to use every tool available? Not remove or dismiss them. Now, it's possible that one day stereoscopic vision could outpace Lidar in cost, reliability, and ease of maintenance. But until we reach that milestone, should Tesla be putting this technology directly into the hands of everyday drivers? Or should it be perfected first before hitting public roads? So if Tesla is betting everything on vision, what are the others doing? Companies like Waymo, Cruise, and TuSimple have taken a very different approach. Their vehicles don't try to solve the entire driving problem everywhere, all at once. Instead, they focus on level 4 autonomy, vehicles that can operate without a driver, but only in tightly controlled environments. The secret behind their success? Redundancy. Waymo's cars are equipped with Lidar, radar, ultrasonic sensors, and multiple cameras all working together. But even more important is geofencing. These cars only drive within pre-mapped zones, like certain districts in Phoenix or San Francisco. Every road, every turn, even traffic light timings. They're all part of a high-definition map. Yes, these maps are expensive to build, and yes, this limits where the cars can go. But what you get in return is predictability. And in over tens of millions of miles driven, Waymo's driverless cars have had 0 reported fatalities. TuSimple operated in the freight industry and demonstrated fully autonomous highway runs without a driver, even in the vehicle. Compare that to Tesla, which still operates at level 2 autonomy. That means the car assists, but the driver must stay alert and keep their hands on the wheel. Yet despite this, many users treat Tesla's full self-driving beta as if it were truly autonomous, sometimes with tragic consequences.
On October 10, 2024, Universal Studios in Burbank, California, played host to something a little different. Tesla's We Robot party wasn't your typical car launch. Instead, it was a futuristic showcase, an immersive event complete with music, lights, drinks, and bold promises. Elon Musk stood at the center of it all, unveiling a new line of artificial intelligence-driven products, the humanoid robot Optimus, the Robovan, and perhaps most notably, the Robocab. If you missed the headlines, the Robocab is Tesla's entry into the autonomous ride-hailing space, a direct competitor to companies like Waymo. The goal? To begin trials in Texas and California by 2025, with full production aimed for 2026. Though, as always with Musk, timelines tend to shift. As of the time of making this documentary, Tesla has officially announced that Robocab trials will begin in Austin, Texas in June 2025. But here's where things start to get complicated. While Tesla has quietly reintroduced radar into its premium models, the Model S and X, it's been reported that the Robocab service will be based on modified Model Y vehicles, equipped with Tesla's vision-only system. That means no Lidar, no ultrasonic sensors, and, according to some sources, not even radar. And that's where the real concern lies. These vehicles are designed to carry members of the public, without a steering wheel, pedals, or any means of manual intervention. In the event of system failure, there is nothing a passenger can do. It raises an important question. If Tesla is entering the private hire market, even if just as a proof of concept to sell to companies like Uber or Lyft, why not include additional safety sensors? Especially when the vehicle is fully autonomous and has no physical controls at all for steering or braking. In a race for autonomy, cutting corners on sensors might save money, but when real lives are involved, shouldn't safety come first?
To understand why Lidar can matter so much, NASA engineer turned YouTuber Mark Robber ran a simple but telling experiment. He compared the accuracy of different sensor technologies in real-world conditions. His results showed that Lidar, while not perfect, consistently outperformed vision-based systems, especially in low light, rain, or when visibility was obscured. So while critics often point to Lidar's cost as a reason to avoid it, the question remains, is cutting corners on safety really worth it? Especially when lives are at stake. Waymo may be slower to expand, and its reliance on HD maps means it can't operate everywhere. But in the areas where it does drive, it's done so quietly, safely, and without loss of life. And perhaps in the race for autonomy, slow and safe is exactly what we need.